In the last couple of videos, we covered the experimental results of the ideal gas laws. We're now going to consider one of the great achievements of classical physics, kinetic theory. Kinetic theory has had a profound implication on the quality of life because our ability to harness energy has greatly enhanced our lifestyles and extended our life expectancy. But it's also one of the great achievements in helping us understand the quantum world and to develop new fields of physics. So we're going to go and do this for a couple of reasons. One, because we want to understand what temperature really means and the ideal gas laws, but also because we want to understand how physics advances and to have a deeper understanding of where physics and engineering are going. Kinetic theory takes advantage of the stuff that we did previously back in energy, momentum, and force. So it's going to force you to actually quantify those things and refresh your memory on them. It was developed by two people, the Scottish physicist James Clerk Maxwell and the Austrian physicist Ludwig Boltzmann. We'll talk about Maxwell more in E&M. He is a profound, great physicist, maybe the greatest one between Newton and Einstein. Boltzmann was extremely important because of his work in statistics and the idea of atoms, and in fact he was the champion of atomic theory. Unfortunately, he suffered from depression, and as an Austrian, he was often attacked because people did not believe in atoms, contrary to what you might hear, until nearly into 1905 it was a hot topic of controversy. In 1905, he committed suicide, hoping that his work would continue without anyone having to give him credit, especially the Germans. What he didn't know is a young German physicist had produced a PhD showing that atoms explain Brownian motion and convincing everybody of the atomic hypothesis. His name was Albert Einstein. I guess what this shows you is that if you get behind in your studies or your homework, it can kill you. To derive the ideal gas law, we're going to need to make some assumptions. These assumptions are the gas consists of a large number of molecules, which it does, that the molecule atoms will move in continuously random motions. Separation between the molecules is large. This is equivalent to low density, so between them they kind of move independent of each other. In fact, we will assume that molecules do not act on one another at a distance. In other words, we're going to treat them as free particles as they move through the container until they collide with either a wall or one of themselves. All collisions between molecules and molecules in the wall will seem to be elastic. That is, we'll treat them as hard spheres, though these collisions will conserve energy and linear momentum. Alright, with those assumptions and nothing else, we're ready to derive the ideal gas law. Consider a cube of length L containing a gas as shown. There are a whole bunch of molecules inside of this thing, going in all sorts of different directions. Like that, and so forth. We'll take one of them, and we'll only consider its motion in the x direction for now. Let's say that it's going with some speed v sub I in the x direction. Then its momentum about to strike that would be px sub I, where that's the x component of the momentum of the ith particle, so I could be 3. Is equal to mass, and they're all the same particles. They have the same mass, but they may have different speeds. So in the x direction, he has some speed vx sub I. He strikes the wall, and when he strikes the wall, he bounces back. And to conserve momentum, because the wall is so much more massive, he basically bounces back with the same speed, but in the opposite direction. And we know this from back in the chapter on collision. So if you forgot this, when an object strikes a big, much more massive wall, the ball bounces back. So if you throw a ball at the wall at 5 meters per second, it hits the wall, it comes back at you at 5 meters per second, but in the opposite direction. So P sub x final can now be found. As minus mvxi. Now the momentum transferred to the wall, delta p wall, is minus the change in the momentum of the particle. So this is going to equal 2 times the mass times Vx, whatever that speed was. This is just minus this minus that. So I have minus mvxi minus mvxi is minus 2 mvxi, but I threw away the minus sign because I'm looking at the momentum transfer to the wall, which is in the positive x direction, and not the momentum transfer to the particle in the negative. This is a consequence of Newton's third law, that if the force by the wall changes the momentum of the particle in one way, the particle applies a force equal in magnitude in opposite direction, changing the magnitude of the wall in the other direction. Now, Newton's second law applied to the wall says that the force on the wall due to this particle is equal to the change in the momentum of the wall divided by the change in time. So that would be 2 mvxi over delta t. Now, if we could build a force meter, there would be some dial here, and this dial would wiggle back and forth very fast. So 1, 2. Because each time the particle hit the wall, then it would apply a force, and it would get a force, and it would differ in values depending on the speed that the particle had that came in and how long it took to interact. Now, it turns out that there are 10 to the 26 or more particles banging on this, so this thing is vibrating incredibly fast. No macroscopic needle or device that we build would actually see this. It would average this over some much longer time. So instead of the interaction time, what we're going to consider to be the time is that the force is constant and that it's over a time in which the particle goes from one side all the way to the other side and back. So in other words, it's the time between collisions by the same particle. Now, if we do that, if we consider this to be the time between repeat collisions, then delta t equals the distance over the speed. The distance is 2 times the length of the container, and the speed is vxi. Again, what I'm doing here is I'm saying that this particle has to go this distance L and then go back a distance L before it can strike the wall again. So the time between collisions is 2L over vxi, and that's what I'm going to take to be the interaction time. Now I'm going to put that into my equation for force, and when I do that, I get delta P over delta T. I got to go up here and pull my equation from a minute ago, which is 2mvi over delta T. So I got 2m vxi, and then I divide that by 2L and another vxi. And I want to take the average of that, because obviously different particles will come in with different speeds, so this force will still be varying. So I want to average that over an average speed that the gas particle might have, and we do that by putting a bar over it. When you average one side, you have to average the other side. So this is equivalent to, I'm going to take the 2 over L out front, 1/2 the mass of a particle times the average of the square of the speed. Now you may ask, why don't I have to keep the average over the mass? The mass is constant. So all the mass is the same and never changes, so you don't have to worry about it when you do an average. It's like if everybody in the class made 100 and there were 5 people who made 100, then the average is 100. It's only things that are varying like 52, 48 and such that you have to add up and figure the average. So we can pull this out. Now this kind of looks like kinetic energy, 1/2 mv squared, but this is only the x component of the velocity, not the total. And this is only the average force of one particle, and there are 10 to the 26, or how many? In our case, we'll say there are n particles. So to find the total force, we're going to have to multiply the force of one particle by the total number. And since we said this is the average force, to find the total, you take, just like a class, you take the average score multiplied by the number of students, you get the total number of points. Here we take to find the total force, we take the number of particles times the average force of one particle. So number of particles, average force of one particle. And this says that our number now is 2 times the number of particles over the length times 1/2 m times the square of the average speed here. I should say the average of the square of the speed along the x direction. Now, using the definition of pressure, we have P is equal to F over area, which is F over L squared. So we have 2 times N over L cubed times 1/2 m Vx sub I squared averaged. But something else is interesting. Look at this, L squared. Well, that's just volume. So we could bring that V to the other side of our equation. So now we have PV is 2 times N times 1/2 mVxI squared averaged. Notice that we've already got the left-hand side of the ideal gas equation. And all we've been doing is applying Newton's laws and definitions from earlier in the course. In general, a gas molecule will not only be moving in one direction, it'll be moving in 3 directions. So the kinetic energy, K, is equal to 1/2 m V squared, which is 1/2 m the velocity dotted with itself. Now I remind you that's the same thing in Cartesian of 1/2 m the x component squared, 1/2 m the y component squared, and 1/2 m the z component squared. So this means that if we average this, we've averaged that, we're averaging each one of these components of the speed squared. But there's no preference in an individual direction. So Vx squared average should be the same as the average of the square in the y direction and the average of the speed component in the z direction. So K, 1/2 mv squared averaged is 3 times 1/2 mv x squared averaged. Substituting this into our relationship back up here, and we get that PV is equal to 2/3 N times 1/2 mv squared bar. And that's the kinetic energy per molecule. We'll continue this in the next video.